Okay, great. All right, so I'll roll. Here we go. So, hi, I'm David Clement, and I've been involved in computer graphics and data computation for a very long time. It's actually about 40 years now. I started in my early teens, so I've been doing this for a very long time. This particular paper is of keen interest to me because I've been working, and I continue to work, in the interface between virtual characters, real people, and robots. So I'll just walk you through a little bit of my background first. But this is what I'm hoping to cover in the next 30 minutes. So we've got just a quick introduction to me and my background, which I've already started. We're going to cover off on what are character models and animation. I'm going to touch on reinforcement learning and then touch on another very interesting area called phase function networks, which is all precursor work to the DeepMimic paper itself. And in the DeepMimic paper, I have to cover the related work because it's crucial to understand the paper itself. You have to understand some of the work that's done prior to that. I'll then do a quick dive into what the DeepMimic paper talks about, the reward structure that's novel, and the contributions that the paper offers. Then there'll be closing comments and Q&A. Okay? So I'm just going to jump right in. So this paper falls in the domain of a large area of research which spans many different disciplines. And the basis of the work is this idea of having realistic agent-based character interaction. So we want to be able to create characters in games that are virtual or real robots or even distant representations of ourselves that allow us to interact with characters in a natural and easy way. So I'm just going to walk you through what's going on here. This is some work I did a few years ago. And what you can see here on the right is an actor wearing a motion capture suit. This is a motion capture studio here in Vancouver. And what you're seeing in these two views in the front here is what the gentleman wearing the VR headset is seeing. And so when I run this video, you'll see that there is a very natural interaction between this virtual character, which is the only thing that the person wearing the headset can perceive, and the real person. So this is kind of like the ground truth that we want to get to with these agent-based systems. All right, we want to be able to produce agents that can interact with us and with their environment in very realistic ways, so that we're not constantly saying, "Oh, that's a robot," or "His feet are sticking through the ground," or whatever it might be. All right, so that introduces a whole bunch of different concepts. So this character that you see here in the bottom left is basically a skeleton where the bones are fixed in length, and the only thing varying from frame to frame is the angles that the various different bones have to one another. And then that's mapped onto a mesh, which is the skin. And what we're doing with things like DeepMimic is we're replacing the actor wearing the motion capture suit with a real-time agent. Okay? So that's some work I did a while ago. More recent work is this work, and this is a telerobotics application. And what's going on here is that I built this robot here on the right, and there are these two cameras. And I'm operating the robot remotely as if I was inhabiting the robot. There's quite a bit of research on this work. And so I actually take control of the robot using the virtual hand controller. And it would have been great to have an agent to sit between me and the robot to make its motions realistic and more plausible. And that's actually one of the reasons I got involved in the machine learning movement, is that this is actually incredibly difficult work to do without having assistance from something like machine learning. And the simple task of just picking up a ball remotely and dropping it into another container was actually very, very challenging. Okay, but once again, this is exactly the same problem where we have humans interacting with virtual characters, or real characters, in this case a robot, and we want to have this kind of smooth, seamless interaction that has very natural physical motion between the two systems. Okay? All right, so, okay, so now I'm just going to do a very brief introduction to reinforcement learning for those that haven't touched on it. So reinforcement learning is different to supervised learning. In supervised learning, you obviously have the immediate reward and a bunch of images or sound bites or some other reference data set as your training data. And in reinforcement learning, that's not the case. In reinforcement learning, you essentially have an environment and an agent. And so the agent is, in this situation, a machine learning agent, and the environment is a physics simulation. And the way it works is that the agent is passed the state of the environment, and then based on its internal model, it then decides and executes a given action. And that action over here on the right then changes the environment. So if I decide to take a step forward, then the environment is changed because my body has moved a step forward. The environment then sends the agent the updated version of the environment. So the new state is passed to the agent. And critically, another piece of information is passed back to the agent, which is a reward. And by reward, I mean a number between 0 and 1, which says that particular action that you took was either good or bad, or none of the above. Now, reinforcement learning is a large area, and two of the authors of this paper, Peter Abeel and Sergey Levine, both of whom have been interviewed on Sam's podcast in the past, are clear leaders in this area, and they're out of the Berkeley, Stanford OpenAI camp in San Francisco. So there's quite a bit of theory behind this, and we do actually have to touch on that because one of the key innovations in this paper is actually related to machine learning. So I'm just going to go a little bit deeper. By the way, this is called the Markov decision process, this loop that I'm talking about here. So I'm actually going to try and explain reinforcement learning in terms of this game. Okay, so this is a game called Sequest, which has been mastered by a reinforcement-based system. So let me just explain what's going on here. So there's this submarine, which is you. And when you go to the surface, you fill up with oxygen. Okay, but when you're on the surface, you can't actually increase your score. And so the reward for going to the surface is the oxygen, but it's not actually the overall goal of the game. If you just stay on the surface, you won't win. And so the game really is, to get the actual score component, is you have to shoot the fish and rescue the divers and avoid the submarines trying to kill you. Okay. And so these are immediate rewards. These are rewards that are occurring in the very near time frame. But there is a more distant reward, or negative reward, which is running out of oxygen, in which case you would die. And so you have to balance these near-term rewards with distant rewards or long-term rewards. And that's the unique capability that reinforcement learning can offer, is that it has the ability to handle what are known as sparse rewards, where rewards are actually quite rare. Okay? So just to go into the math just for so here is an experiment I did about 4 months ago in OpenAI Gym, which uses reinforcement learning. So this agent on the floor here is just a physics model of a character. And the only rule I've given it in this particular scenario is try and keep your head as high as you can for as long as you can. So the higher your head, the higher the reward. It's just that simple. And then when you run the simulation, you see that it starts off not having a clue how to achieve the reward. But after 16,000 episodes, it's actually able to bounce and basically sit up. And then as the number climbs higher, it develops these strategies to stay higher longer. So all of this behavior is completely discovered by and being executed by the agent. I didn't teach it to do any of these things. And that really is a remarkable achievement the remarkable achievement that reinforcement learning offers. So there's a couple of key concepts here. There's something called a trajectory. It's also known as a rollout. It has other names. And really what that is, it's just a sequence of state and action, state and action, state, action, state, action, state, action, state, and so on. So if you consider that you play a computer game, that could be considered a trajectory or a rollout, okay? And the way that you learn the game, which is basically the same way that these agents learn the game, is they start off playing it poorly, they get rewarded for good things, and they get negative rewards for bad things, and they do it again and again and again and again. And so you might have a million trajectories or more. And this is where we get into sample efficiency, which I won't be touching on, but it's a very interesting area. So instead of exposing our neural network to images or to structured data like we did in the Fast AI course, this is very different, because what we have is a simulation, or we have the real world in some rare cases, and we're training our agent to navigate through a very complex environment which may have basically an infinite number of states and an infinite number of actions. And there's another very important concept, which is this idea of what's called the discounted sum of future rewards. So the discounted sum of future rewards simply means that when we take an action, we not only have to consider the next moment in time, but the far future as well. But when we consider the far future, we have to essentially bias our actions towards the near term because those are more immediate benefits or rewards over the long term. Okay, so in that game I was just showing you, if you have a full oxygen tank, then that is a very distant reward and should be discounted. You don't have to worry about oxygen for quite a while. And more near-term rewards, like shooting the submarines or avoiding the missiles or rescuing the diver, have a higher value in the near term. So there's this concept of discounted sum of future rewards. So down here you can see that when you calculate a reward, you have this discount factor, which is applied at time 0 for the reward at time 0, and then it also considers future times and the rewards offered at those future times. But these future rewards are discounted by this gamma, the concept of this gamma discount variable. All right. So that's all I'm going to go into with reinforcement learning. I can talk more about it if you'd like. I'm going to skip this for now because I'm not sure how far we can get. So there's another novel concept that's used in this paper which I hadn't seen before, which I'll share with you, which is the idea of a phase function neural network. And what this means is it's very similar to an RNN, where you have essentially a clock which ticks, which is called the phase function. And then as the clock ticks, the weights are essentially switched out for each tick of the clock, or new weights are, blended in using a Gaussian or something like that. So I'm just going to jump to the next slide here. So on the right, you can see a picture of the neural network. And if you look here, there's a dark line. I don't know if you can see that, but it actually repeats. I don't know if you can see my hand, but it actually repeats as the phase goes around. So this isn't one neural network. This is actually a collection of neural networks where each phase, each step in the circle essentially has a separate neural network associated with it. And that allows you to deal with cyclical functions like walking or doing complex maneuvers like side kicks and backflips. And in fact, the DeepMimic paper would not be possible without using these phase function neural networks. So what I'm trying to get at here is the ultimate goal of the paper, because I'm not talking about the whole field right now, the whole domain. I'm specifically focused on the goal of the paper, and there are two goals. So on the left here, you can see that we have an agent that's interacting with the world. It's avoiding the obstacles. Its feet are sticking to the ground, and it's moving in a natural way. Okay, so that is a kind of a generalization of what it is to exist in the world. All of us do these things, and that's what looks natural. On the right, what I'm trying to get at is we want the ability to direct the agent. Even though it's acting in this natural way, if it's just a pre-recorded animation, it's not very interesting. So we want the agent to have the ability to take different paths and make different choices as it needs to. And these are the goals of the paper. All right. So this is the paper, and as you can see, this character, for the very first time that I'm aware of, which is a reinforcement-based learning character, is able to perform very complex maneuvers. So now I'm just going to go briefly into the lead up to this work, because there's been some very, very deep work done in the past in this area. So this particular piece is done by Libin Louis, who's now at Disney, and Michael van der Pan, who's out at UBC here in town, and their student Kang Yin. And this is, I believe, the first time that they were able to train using neural networks, they were able to train a physics simulation to perform complex maneuvers, okay? So that's a key component in the DeepMimic paper, and that was done a while ago. Another key piece of work which was done by Shailen Agrawal is this piece, and I just want to stop and explain what's going on here. The idea is that you have a series of predefined tasks that you want your agent to perform. So make a cup of tea, pick up the box, sit down, these kinds of actions. And then the system has the unique ability to smoothly and realistically blend between these tasks that are essentially finite. So you have a finite state machine, and the agent is able to move very smoothly through the finite state machine in real time. Okay, so this is from 2016. And then two landmark papers came out in 2017 at SIGGRAPH, which I had the good fortune to attend. One of them was Deep Loco, and Deep Loco really is the precursor to DeepMimic. It's done by the same people.
Motion control is a challenging problem.
I'll let him speak for himself.
Nearly all previous solutions make use of high-level features, such as the center of mass, some high-level structure, such as a finite state machine.
It's pretty quiet.
Sorry. Okay, so essentially what he's saying is that they are using deep neural networks as opposed to past methods in order to train the system to drive an avatar through very complex environments. So the only goal that's being specified here by the operator is the red line, which represents the goal of the agent. And the agent is able to smoothly navigate a complex world. It uses what's called a hierarchical learning system. So you have a high-level controller which operates in a long time frame, and a low-level controller which operates in a real-time way. And these are able to drive a simulation, so I won't dwell on that too much. And then the other landmark paper that came out at SIGGRAPH was this one, which was using phase function neural networks to control a character in real time. And to the best of my knowledge, this is the first time that a player is able to navigate a character over arbitrary terrain, and for the character to act in an extremely natural-looking way. This is remarkable work out of the University of Manchester, and really DeepMimic is the synthesis of the Deep Loco paper, which I just showed you, and this paper. So these are the precursors to the DeepMimic paper. There is another paper which unfortunately I couldn't show because it's under copyright by Disney. Libin Louis has moved to Disney and is doing research there now. And they did some remarkable work which is similar but different in important ways from this. Okay, on to DeepMimic. So, what is DeepMimic? I mean, what are we doing here? So, in their own words, DeepMimic receives as input a character model, similar to what I was showing you earlier when I was in virtual reality, a set of kinematic reference motions. So if you can imagine that motion capture actor I showed you earlier performed a series of motions and we recorded those, we can consider those as training data for the agent, all right? And then the final thing, which is why this paper is novel and different from past papers, is this idea of a task. So not only must you very accurately mimic human behavior, but you also have to accomplish a task at the same time. And you have to find a happy balance between looking believable and plausible while achieving the task. So I'm just showing you some examples of this. And so really what DeepMimic is, it is a technique for creating the controller that can drive these characters, okay? So DeepMimic isn't a product, it's not a neural network, it's a technique, all right? It's a way of approaching, taking pre-recorded examples of motion and a character and certain tasks and bringing those together to form a system that can essentially manufacture an agent that can drive these characters in real time. Okay? So that's what the paper is trying to do. So in order to achieve that, it does use reinforcement learning, and it does use all the other components that I was referring to earlier. But I think that it's key that we can dive in and just consider a couple of different things. So the reward then of the system, like the reward I was showing you in the game earlier was don't die, get a high score, rescue divers, shoot bad guys, shoot fish. These make up the reward. In this situation, the reward is made up of two parts. The first part is the reward is essentially the smaller the difference between where you are and where I want you to be, the higher the reward. So the agent is rewarded for mimicking the behavior as closely as possible. And that's very interesting and very powerful, because it doesn't have to be perfect. As long as you're getting closer, then the system will essentially do its best to mimic the desired behavior. And that's a very powerful idea. So this term on the left here is the imitation objective. The term on the right is the task or the goal objective. So I want you to kick the ball or throw the ball through this target, or, land safely, or whatever it might be. And so this is the directability I was talking about earlier. So this is the generality, behave in a natural way, and then the goal is I want you to achieve this outcome while doing this. So the policy that they're using is very interesting. I just want to touch on this once again.
Hey, David, before you do that, do you have a minute for a couple questions?
No problem at all. Go right ahead.
Nick is asking about, are any of these examples developing their own physics engine, or is the learning primarily for the purpose of developing agents to interact with existing physics engines?
So this particular work was done using Bullet.
Bullet?
A Bullet is a physics engine, an open source physics engine.
Okay.
That's very powerful. But I can honestly say that there is no strong connection to a particular physics engine. And one of the examples that they have in the paper is they take the agent and they put it in a different gravity setting. So you can alter the physical characteristics of the environment, the physical parameters of the simulation, and the agents still perform very well. And I will bring up, there is another very interesting physics engine that's available called Majoku. And Majoku is really interesting because it can deal with contacts. So one of the problems in computer games is the idea that you can't have friction when you roll on the ground and other things. And Majoku really is a novel physics engine in that regard, in that it allows you to have much more accurate simulations. And the simulation I did earlier was actually using the Majoku engine. But there are different frameworks that use different engines. I hope that answers the question.
Yep. And then on the previous slide, you've got the two terms, one of which is the task-specific term. How is the task specified?
Excellent question. So the task is specified, to the best of my understanding, as what is known as a sparse reward. So the agent doesn't receive any reward for approaching the target or for getting ready to go to the target. The only reward the agent would receive is achieving the outcome. And if you watch the supplemental video, there's a section in there where they show how the agent achieves the objective without doing the mimicking. And it's very interesting in that it instead of throwing the ball, which was the action that it was told to mimic, it's just, it's told to achieve the objective. And it basically picks up the ball and runs and pushes it through the red ball in order to achieve the objective. Yeah.
Okay. Any other questions for David? All right.
All right, I'll carry on. That's fine. There's not too much more to go, actually. I'm just trying to keep this tight. So this is very interesting. So you were just asking about the goal, and this is exactly what these two terms here is. So these are both fully connected networks. So the 1024 ReLU, this is the ReLU symbol here, is fully connected to a 512 ReLU, which is fully connected to just a standard linear outcome. And the goal is actually fed in here. So if you achieve the objective of the goal, then you receive a strong reward here, and so on. This upper path is very interesting. This is actually what's known as a height map. So if you imagine you are measuring the elevation at every pixel around where the agent or the character is standing, that's exactly what this is. So this is an image, it's the two-dimensional image, but instead of being the color of the ground, it's how high it is. And then this goes through a standard convolutional neural network where you have an 8x8 ReLU layer, it goes into a 4x4, and then another 4x4, I believe this is the pooling layer, and then this goes down into the fully connected network as usual. So these policies are actually quite reminiscent of material we covered in the Fast AI course. So it isn't that exotic. It's not like these things are completely foreign if you've done that course. And these are what's driving the agent. So there are three main contributions that the paper has made, and I just wanted to cover each of, well, four actually. The extensive evaluations I can't really cover because it's just the fact that they did an ablation study on this. You can look at the paper for that if you're curious. Reference state initialization is very interesting, and then I'll cover early termination and multi-clip integration. So let's just jump into reference state initialization. So here you can see we have a trained policy, and as you can see, the simulation was able to mimic the training clip with very, very high proficiency. And that's great. But that was actually done years ago in the previous paper I showed you. So that's actually not innovative. Okay. Now, what happens when you don't have reference motion? Which is
not bad.
Sorry, you had a question? Sam? Sorry. So when you don't have a reference motion to mimic, the character develops these very weird idiosyncratic behaviors, similar to what I showed you in my experiments earlier, all right? So that's the benefit. Whoops, sorry, that's not what I wanted. I'm going to go back, sorry. Yeah, so, oh, it's crashed. All right, I have to restart PowerPoint. This is a bug, sorry. I just have to restart PowerPoint. One moment, please. It crashes when that happens.
All right, while we're doing that, if someone had a question, feel free to unmute now. It sounded like background noise, so I did mute it. But if you do have a question, go ahead.
All right. Screen share. And PowerPoint. Sorry. PowerPoint, where are you? Oh, there we go. Okay. Yep. Sorry, I'm just trying to get back to where we were. Sorry about that. Okay. All right. So I just wanted to play the video, and hopefully it won't crash this time. There we go. Okay, good. All right, so we're back on, and that's great. All right, so in this situation, you can see that we're able to accurately achieve the backflip. However, if this thing called, without reference state initialization, it actually very accurately mimics what would happen if you asked, you know, a young person to do a backflip without any training, which is, oh, we jumped again. Goodness, one moment, please. I have to be careful here so it doesn't crash again. There we go. All right, so I have to use this control. Yeah, so as you can see, the character kind of lurches backwards, but can't actually achieve the backflip. And no amount of training actually allowed it to do so. And so the key insight here is this idea of what's called reference state initialization. So what they do is imagine that you're standing in front of a huge hedge maze and you're trying to find the answer. You're trying to solve the maze. What they're suggesting is that you just, if you have a solution to the maze, you actually just start them off at different points along the solution to the maze. So in a backflip, you can imagine that you might start halfway through the backflip. So I'll just play for a moment So you might start at this point, or you might start the simulation at this point. So if you start the teaching at this point, it will learn how to land. And if you start it a little bit beforehand, it will learn how to essentially do different parts of the flip. And this is a key insight that was not known before, I believe. So if you are trying to train a network, specifically a phase function neural network, to achieve a very complex maneuver, you can actually, by training the policy randomly starting at different points in the reference material, you're able to train it much more effectively. In fact, you're able to train it to achieve the goal, which otherwise is impossible, by doing this particular thing. And a visceral example of this to me is this particular thing, which is this young girl here clearly would be at great risk if she tried to do a triple forward roll in a swimming pool without any training. And so in much the same way that you are teaching the agent different aspects of the jump at different times, the coach here is clearly training her how to do these different maneuvers. And this is called curriculum learning. There's another field in deep reinforcement learning called curriculum learning, which I'm not going to go into any depth on. So that's one key finding that they had, this idea that if you're training an agent to mimic a complex behavior, the best way of doing it is to randomly start the episode at different points during the successful simulation, to the successful trajectory. The second innovation is what's called early termination. So what this means is that what's happened here is the character has fallen on the ground already. So early termination is these episodes or trajectories that you go through are very expensive. Physics simulations cannot be multi-threaded, and so these things don't scale well at all. You actually can't use GPUs to accelerate these simulations because the whole idea of a physics engine precludes that kind of mass scale out. So in order to make these trainings efficient, you have to try and have very good sample efficiency. And the second finding they had was not only do you need good sample efficiency, but if you let the simulation run long on essentially bad trajectories, it actually damages the overall training of the network. So what they developed was essentially a set of safety guidelines. You know, if my head hits the ground or if my hand hits the ground, then stop. Don't bother trying to learn anymore. Just end this episode with a negative reward for that last little bit of it and try again. And so that's this idea of early termination. When they introduce early termination, they are actually able to successfully train the agent to do the backflip. All right? Otherwise, they couldn't get it to work. So when you have these two, then you're able to achieve the outcome, which is actually very useful and a really interesting outcome. Okay.
Is part of the idea here that without imitation, it's too hard to specify a reward that causes the agent to do the backflip? Like, we don't know how to specify that, you know, the head needs to be under the body and kind of guide the agent to doing the backflip through the reward function?
Exactly. It's extremely difficult to do it by hand. Like I've hand animated characters for donkey's years, and it's a full-time job. It's extremely time expensive to have a human being sit there saying, okay, move a little bit, now do this, move a little bit. Oh, it doesn't look realistic, or the physics doesn't work, or it's a nightmare. And so the ability to use data to drive these animations is huge. Like, it's a massive industry-changing innovation, and the ability to have these agents to be steerable so that you can direct them, and to have them robust so that if there's something in the way, they'll move around it. If there's the stair, they'll put their foot on the stair. This is huge, and because you're training it from natural human behavior, the behavior that the agent exhibits is natural, and that also makes these agents, in terms of robotics, much more comfortable for people to be around. Like, if I'm in a room with a robot that's behaving just like a human, it's not going to set off the same alarm bells as it would as it was kind of thrashing around, and I couldn't make predictions about its behavior.
Yeah.
So the third breakthrough of the paper was this idea of multi-clip integration, and this has been a holy grail for a long time, and it's actually a very hard problem. So the idea here is that on the left you have these three clips, all right? So you have this clip of the gentleman taking a step forward, the gentleman turning to the right, and the gentleman turning to the left. And as we move through this, you can see the agent on the right is able to smoothly turn corners and interact in a very continuous way. And the way they did this is really interesting, is they trained three separate neural networks. They trained one to smoothly turn right, they trained one to smoothly turn left, and they trained a third neural network to take a step forward, and then they essentially blend them at runtime, which I thought was very novel. So there's no actual training in the blending. They just kind of do a simple linear blend, an alpha blend between the different motions, and they're able to achieve very realistic results, which is very cool. Now this is also useful in something called retargeting. So this is the Atlas robot, and the interesting thing here is this is a physics simulation. So the Atlas robot is a giant beast, like it weighs 3 times as much as I do. And the fact that they're able to train an agent to mimic human behavior on something that is, from a physics point of view, is nothing like us, like its arms are heavier, its torso is heavier. Because these neural networks are so general, you can actually train these agents to drive these giant heavy robots so they look real. And similarly here, what's going on, and this is a key frame here, is the agent is able to, in real time, retarget its footsteps so that it doesn't fall down the cracks. And that's a really amazing behavior for these things to do. Footstep planning is a huge field all in itself. Michael van der Pan is a real leader in that research area. So this is another very key innovation which I have not seen before, which is they're not actually even using reference data now. So what they've got is they've had somebody hand animate a T-Rex and a lion in a conventional way, and then they're able to train a neural network to essentially bring those pre-recorded static motions to life and to essentially breathe life into these agents. And they look very much like a T-Rex or a lion, which is, once again, quite remarkable. Okay, so that was multi-clip integration. All right, so I'm basically done my first pass. So really the main contributions that this paper offers very quickly is reference data initialization. So that's the key concept here is that if you are training your network to mimic something, anything, then you should train your network by starting at different points throughout the thing that you're trying to mimic. Okay, this is a key insight that the paper offers. Secondly, if your deep learning algorithm has reached a point of no return where essentially it's failed in its outcome, there's no point in continuing. You should stop that particular trajectory right away and focus your resources on other trajectories that may yield better results. And thirdly, if you do train neural networks to mimic some pre-recorded something or other, whatever it might be, human motion, or it could be anything. It could be a valve opening and shutting. If you've trained your neural network to do that, and a variety of other motions, you can actually just, through simple linear interpolation, blend the outcomes of these different trained networks to produce very good results. And the final thing, which I can't share with you, is they did a lot of work on this. I would highly recommend that you watch the supplemental videos. I pasted them all into the TWIML meetup channel. And I'm available for questions and answers.